these are two examples of real biofilms that I have grown. And these pictures you see under SEM microscope. In both of them, the substrate is carbon steel. In one on the left, it is sulfur-reducing bacteria that have formed the biofilm, and the one on the right has been formed by iron-reducing bacteria, IRB. As you can see, the surface is, doesn't look like a film. Rather, it has a fluffy structure full of potential spots to create differential aeration cells or differential concentration cells. And that's why in 2020, I published a paper in which I suggested that the term biofilm is incorrect. Why? Because when you hear biofilm, you may assume that 100% of the fabric is biological stuff, which is not correct, and that it is a film, which is not correct either. Instead of biofilm, I suggested a Greek term, temenos. Temenos means cut off, and the rationale behind it is that under biofilm conditions could be vastly different from conditions around it or outside of it. Like, for example, you have an environment which is oxygenated, but under the biofilm, there could be conditions where oxygen has been depleted, or the pH outside the biofilm could be 7, under the biofilm it could be 5, it could be 4, for example. So it is as if biofilm is a cut-off structure. It is a structure cut off from its environment. And I argued that temenos is a more logical terminology than the term biofilm that was coined in late 70s and actually is quite wrong. All right.
Just one question. When you put the anode under the biofilm here,
yes,
would be a kind of additional barrier resistance of transport through the biofilm?
Well, actually, due to fact that this pitting will be filled with positively charged ions, there could be some sort of interactions that would accelerate actually localized corrosion.
You mean the biofilm is a kind of conductive material to...
It is indeed conductive.
Yes, but for the case of hydrophobic bacteria, there might be case of hydrophobic bacteria can be a problem, or maybe some products of biosurfactants product of the biofilm that can make a kind of additional adsorption layer, which can somehow make a real barrier for transport of ions.
Well, actually, bacteria could not be hydrophobe because for their growth and activity, they do need water. And if somehow they have any properties that would allow them to repel water, they will not be able to survive.
But the hydrophobicity somehow is a kind of rational properties. We published 2 years ago one of our paper about hydrophobicity properties of the bacteria that influence its interfacial properties. And to understand the hydrophobicity factor, One way is, for example, you solve bacteria in one phase, like water phase, and then you mix it with uh, um, oil phase, like hexane, for example, or heptane, and then you can see how the partitioning coefficient happen, how the bacteria is distributed between two phases. And we have the case that more than 80% of the bacteria goes to oil phase. This somehow we call that there is a hydrophobicity factor for that.
Well, actually, if I didn't have the uh, honor of reading that paper, but one thing that comes to my mind is that the oil has the oil is a rich source of carbon, and when you compare it with water, bacteria would go to oil not because of hydrophobicity or anything as such, but simply because they are seeking for carbon as a food source. Bacteria themselves in nature, they are treated as negatively charged particles. And actually, this is one of the reasons that sometimes cathodic protection can work against microbial corrosion, because during cathodic protection, you create surfaces negatively charged, and as bacteria themselves are also negatively charged, there could be a repulsion between these two, so that no biofilm formation will be allowed. But it is something that I think this hydrophobic behavior you see from bacteria in oil-water interface could also be explained because, as I said, the bacteria are simply going for food. This is something that we need to further discuss down the line.
Yes, this is actually very interesting issue for me, because the bacteria first should be soluble in oil phase, then can go to find the food there. It means that the surface properties of bacteria needs a certain hydrophobicity, although there might be some group still hydrophilic, depends on the bacteria. But this is very interesting discussion point. Maybe later we can discuss about it. Thank you.
It is. You're welcome.
Sorry, Dr. Reza, may I ask a question?
Please.
Regarding, sorry, I don't have enough knowledge about corrosion science, but my understanding is that for the corrosion, we need the electrochemical pills, and for this one, we need a path. Regarding the picture right now, you are showing the anode is under the biofilms, and for transferring the bacteria from the upper to the under the biofilm, we need a path. Regarding your explanation about that, we need a pitting to bacteria SRB or IRB go under the biofilm. So I can feel that, or I can think the MIC is not the first reason of the corrosion. We need another mechanism to accelerate or generate a path for bacteria. So MIC will be the second corrosion mechanism, not the first corrosion mechanism. Am I right?
Well, actually, there are several explanations and theories coming up since 1932 that it was first attempted to explain MIC in purely electrochemical terms. And what I am presenting here can be categorized as chemical MIC, CMIC, where we try to explain the phenomenon by putting emphasis on the contribution coming from chemical or electrochemical factors. Since 2008, thanks to a PhD student, a Vietnamese PhD student who was working in Germany, we have been introduced to a new concept, a new theory, which is called EMIC, electrical MIC. And simply, I will also explain it to some extent. Simply, it means that all these anodic, cathodic things are all meaningless, because bacteria actually directly sticks on the surface of the metal, and the bacteria itself becomes cathode and sucks up. It starts to suck electrons directly from the metal itself. So the metal itself becomes anode, and the bacteria becomes the cathode. Therefore, if you allow me, I will go through these mechanisms. But whether or not MIC could be a primary corrosion scenario or a secondary corrosion scenario, my experience tells me that in many cases that MIC could be a primary corrosion scenario, enhanced by other corrosion processes already present in the system. So there is always this competition between MIC, like for example, in cases of failure due to hydrostatic testing that I have worked on, we have seen that, for example, the failure has almost always happened on weld zone, on heat affected zone, all right? Now, it is because the bacteria inside the hydrostatic testing water has corroded the weld zone in such a way that, for example, a secondary phase like iron sulfide has been produced. And this iron sulfide phase has been in contact with the weld line, therefore creating a galvanic couple. And corrosion has started from there. These are cases, as I said, sometimes it is MIC that acts as primary corrosion scenario. Sometimes it is acting as secondary scenario. It all depends on the hydrodynamics of the system, if it is a water-containing system, as well as the thermodynamics behind corrosion reactions already taking place.
Thank you very much. It was very interesting explanation. Thanks a lot. If there is no points, we can continue. Right now we passed 1 hour and 30 minutes. We can continue the session for next 30 minutes. Please continue.
Okay. So there are several types of bacteria that are shown here, like for example, SRB, sulfur oxidizing bacteria, iron oxidizing bacteria, iron reducing bacteria, Clostridia, and it is not just all. These are other examples, and all these that you see here have been isolated from the waters of the Persian Gulf, and almost all of them have corrosion effects. I will very quickly go through some of them, but bear in mind that some self-proclaimed microbial corrosion experts, they put rather false information that SRB are the most important or main bacterial concern. It is quite wrong. All right, sulfur-reducing bacteria, SRB. What they do, they reduce sulfate, SO4, to sulfide, S-2. They can induce corrosion rates around 2 millimeters per year or above, and in their presence, corrosion can proceed 70 to 90 times faster. We have some electrochemical evidence for that, in the presence of SRB, pitting potential could be reduced to low values, meaning that the material will fail in a much shorter time. Some interesting things is that SRB can tolerate pH between 5 and 9.5. They can grow at temperatures between 4 and 110 degrees centigrade. They can tolerate atmospheric pressures between 500 to 700 atmospheres. And there are several theories to explain them. One of them was put forward by two Dutch scientists, von Wolzug and Kuhr and van der Vlugt in 1934, that puts the blame on the enzyme that the SRB have. And I'm just going through this very quickly because we simply don't have time. And then this is electrical MIC that I just mentioned. According to this, SRB and some other bacteria, we have seen EMIC for other bacteria too. But bacteria sits on the surface and then it grows nano wires through which bacteria are sucked up directly from the metal. That's why if you look at this list here, we have a range of theories to explain microbial corrosion. At the moment, EMIC is the only one that is acceptable. Actually, electron is taken from the metal. It goes through the conductive iron sulfide film and then received by bacteria. And you can get typical corrosion rates of 36 mpy. As you may know, according to NACE recommended practices, when you have corrosion rates more than 5 mpy, it means that you have very severe, disastrous corrosion. These are iron-reducing bacteria. They reduce ferric to ferrous, and these are that I isolated myself from seawater in Australia. And the way that these bacteria can work together is a good example of teamwork. You can find such details in my publications. I'm not wasting your time. Then we have sulfur oxidizing bacteria. They can produce sulfuric acid with a pH of 1, which is quite the highest acidic naturally produced acid. In some countries like Canada, South Africa, and Iran, we use sulfur oxidizing bacteria for bioleaching of low-grade copper or gold ores, and it is quite productive. Another type of bacteria are Pseudomonas. These Pseudomonas, let me tell you this, many of the bacteria important in the literature of microbial corrosion can also have adverse hygienic impacts, like, for example, as you can see, nail infection in ladies. These Pseudomonas can actually cause infection in urine systems, and they also increase corrosion by facilitating biofilm formation. Then we have methane producing bacteria that they produce methane, and due to production of these methane, there could be always likelihood of explosion. It is interesting to see item number 3. Some methanogenes can promote the growth of SRB and acetic acid producing bacteria. And then you can see they contributing to corrosion. Clostridia are not only important in the literature of corrosion, but they have been They have been known for contributing to gangrene, for example, as you can see here, and they produce ample amount of hydrogen, resulting in hydrogen-induced cracking, as well as producing acids that will lower pH. All right. Then this can summarize what I was going to address: the symbiosis, the teamwork between different kinds of bacteria, which actually would increase the impact of corrosion. And when you have several bacteria, that is mixed culture, several types of bacteria, corrosion will happen much faster with much higher severity than having just one type of it. Like, for example, for a underground pipeline, you could have several types of corrosion scenarios that could actually compete with each other. Or you have two different structures, completely different, a buried steel pipe and immersed steel pipe, and the scenario for MIC for both of these structures is the same. I have explained it in detail in my books, and I'm not going to show more than this. This is an example that we had in Papua New Guinea, where due to impact of SRB and iron-reducing bacteria, we got very severe pitting and corrosion in such structures exposed to low water corrosion. Stress corrosion cracking can also be enhanced by the impact of bacteria. To the best of my knowledge, I was the first who proved that stress corrosion cracking could be also affected by bacteria. Like here, you have carbon steel affected by pure iron-reducing bacteria, shown as biotic. You see that the time of failure, the time to failure when you have bacteria is shortened, meaning that carbon steel can fail in much shorter time than when you don't have the bacteria. There are ways by which MIC can be treated: by pigging, by application of cathodic protection, by use of chemicals, by use of bacteria. These are two examples of PIGs. PIG stands for Pipeline Inspection Gauge. This is one way of dealing with MIC, provided that all the biofilm or temenos basically has been removed. Otherwise, regrowth may happen. You can use biocides, chemicals such as chlorine or aldehydes. I'm not going through all these, but I want to make a point here that as researchers, Chinese guys have been well advanced in using natural biocides. Like, for example, the extract of neem tree leaves, or essential oils, or cinnamon, etc., etc. And unfortunately, in Europe and in the North American continent, we are well behind them. The good point with natural biocides is that because they are coming from nature themselves, in case of any failure and leakage, you will not have that much damage to the environment. Biological treatment of bacteria, simply you promote good bacteria against bad bacteria, but these have their own pros and cons. Well, we have coatings that could be made quite resistible to microbial corrosion. One of the wrong beliefs was that, for example, epoxy resins, the last line, was quite stable towards microbial attack. In 2018, we realized that actually epoxy could be also consumed by bacteria. So there is always room for research. There are two ways by which MIC can be detected, either by traditional culture methods or by molecular microbiological techniques, and they all have their own pros and cons. Like, for example, when it comes to molecular techniques, the second one, DGGE cannot detect certain types of bacteria. So it is always better to use both culture-based and molecular techniques together. There are standards that you can always look at. I am I'm a member of the committee who is looking at NIST standard TM0212 2012 to upgrade it. But let me tell you that none of these standards will be your final answer. They are just guidelines, as all standards are. And there is also room for mathematical modeling mathematical modeling of microbial corrosion, and therefore this is also an open arena for those who want to do certain research. All right, before I start case histories, anything you want to ask?
Thank you, Dr. Reza. There is no point and question or raise hand. Please continue.
All right. Back in 2006, I was called by a nickel smelting company in Australia to look at the condition and assess the condition of their assets for corrosion, and particularly microbial corrosion. As you know, many parts of the world, especially in the Middle East, they are very proud with their RBI, so-called risk-based inspection, and they have done a lot. But when it comes to RBA, risk-based assessment, we are very poor. I did an RBA based on my RBI, and I mentioned that their foil water rings are quite susceptible to have microbial corrosion. They didn't listen. And after 1 month, there was a fire in the plant. And when they wanted to control the fire by using water, because there were a lot of scales and corrosion products inside the pipe, as you see from the picture below, the pump actually could not take enough water, and therefore half of the plant actually burned down. And one thing that could have been solved by something like $50K, they had to pay $1 million to remediate back in 2006. This is an example of very thick biofilm or temenos that has been formed on concrete substrate in a power plant in southern part of a country in the Middle East. And in this power plant, on one hand, they are applying phosphate to basically control corrosion. And this phosphate actually will be used as food by bacteria. Then their only line of defense is application of chlorine, or better to say chloride-containing bleach, chloride-containing liquids. But with this thickness of temenos, no bleach will be useful. So what they do from time to time, they spend a lot of money to just scrap all these biofilms, and for that they have to basically overhaul the power plant for a few days. These are all costs, but instead of that, just by considering the fact for changing chemical treatment regime, they could have easily overcome the problem. This is an example of carbon steel. I think the overall thickness was about 2.5 millimeter or so. It was less than 3 millimeter for sure. And we got these features of pitting with a depth of 2 millimeter caused by sulfur-reducing bacteria. Then this is the book that I mentioned earlier, a pathological mini atlas of microbiologically influenced corrosion and deterioration. And I am honored that I had 15 contributors for case histories from around the world, different countries, different industries. I will share with you a few of them. This, as you can see, has been taken from a bioleaching process, and a slurry containing sulfur oxidizing bacteria and copper concentrate was the fluid, and this poor thing survived only 3 years in service. Then you have this case for a stainless steel welded joint, and the fluid was a mix of treated and untreated raw water with a chloride content of less than 75 ppm, and combination of factors, incomplete weld root penetration, formed crevice. Very important here is inside weld metal, which led to favorable conditions for initiating MIC. As you see here, MIC was the primary corrosion process, resulted with pitting corrosion. Additionally, weld joint surface was not treated after welding. Therefore, you did have rough surfaces that contributed to lower corrosion resistance of the weld joint area. Then we have this case for corrosion in Christmas tree equipment valve body, were temporarily exposed to completion and production fluids and remained with a small amount of stagnant fluid. Therefore, when you have this stagnant fluid, which has a lot of positive or contributing parameters that would increase the likelihood of MIC, it is quite likely that you will get such morphologies. MIC-induced pitting and cracks by hydrogen embrittlement also occurred. This one is showing industrial water distribution system. As you can see, very badly corroded, untreated industrial water, and you have here a case for activity of sulfur-reducing bacteria, iron-reducing bacteria, and acid-producing bacteria. Last but not least is this flange joint, where raw untreated water with maximum 140 ppm chloride ion and with increased iron and manganese content was the fluid, and it happened during hydrostatic testing. Although the water has been treated with ultraviolet UV, it didn't work. So this is a warning sign for those operators and professionals who think that by application of UV, the water will be highly safe to be used. SRB bacteria occurred during hydrostatic testing, and this asset survived only a few months. This is a case in one of our power plants in western part of this country in the Middle East. The green layer of algae has covered this composite material. It is a case of biofouling, and it has happened 1 year after the power plant started using city sewer output. In some countries where there is water deficiency, they prefer that they take the city sewer water, they treat it chemically, and then they use it as processed water. If the treatment is insufficient, you will end up with cases as such. And this has happened almost 1 year after this. And the picture that I took was after 3 years, when the plant had shifted from using well water to municipality sewer water. Okay, this is the last slide. Before I talk about the slide, is there any questions you want to ask?
Thank you, Dr. Reza. Any participant, if you need to share an idea, yes, please, Ahad, go ahead.
Hello again. Thank you very much for the nice presentation. My question is it possible to have just MIC as a corrosion factor in, for example, in laboratory? We just have MIC, not other influential parameters.
Yes, it is possible, at least under laboratory conditions. Yes, it is quite possible. And thanks to this opportunity, I got my PhD.
Thank you, Dr. Reza.
Thank you.
Okay. Dr. Shafi, do you have another question?
No, just what I was thinking that as a materials engineer, actually, when I saw, for example, the flange that was corroded by water or something else, yeah, for example, this one, is it possible scientifically that we can conclude that, for example, 30% of this corrosion is caused by MIC, and I don't know, the other portion caused by the regular corrosion, or not? It's not possible to say something like that.
Yes, you can. If you look at the color of the corrosion products here, you see that it looks like orange, which is a characteristic color for formation of hematite, Fe2O3. And it is also a sign of having too much oxygen in the system. So yes, it is possible that in addition to MIC, you also have had what you call it, a non-suitable oxygen or non-suitable chemical regime for controlling oxygen. Therefore, you have come up with a mix of reactions. But it is possible that you create under laboratory conditions only MIC related conditions, and see for yourself if it was MIC only that was the main contributor. However, in the long history of MIC research and also standards, they advise that whenever you are conducting an MIC research, it is always better to conduct the same experimentation when bacteria are not present to make sure that what you have measured has indeed been the contribution by MIC. You know where I'm coming from. So that's why they say that do your tests under both biotic, that is with bacteria, and abiotic, without bacteria conditions.
Can I have the second question, or?
Yeah, please go ahead.
Okay, thank you very much. In Canada, that the temperature is almost 8 months of the year is close to 0 or minus. Is it possible to think that, okay, here that the temperature is lower, the activity of the bio products are so lower, and the corrosion rate would be less than the other countries, for example, the Arabic Gulf countries? Is it possible? Is it right or not? This kind of...
let me put it this way. A few years ago, this authority in Canada for gas transportation, I forgot their name, but I was reading a paper where they said that in Canada, 37% of corrosion failures of buried gas pipelines was due to corrosion. 37% of failures in gas pipelines was due to external corrosion, and 50% of this 37% was due to MIC. So what does it mean? It means that if you have bacteria that are still capable of being active under very harsh environmental conditions, you will get MIC anyway. Don't forget that what happened with Purdo Bay disaster, I don't know if you know about it. As a materials engineer, you should know about it. It happened, I guess, in 2006, where the pipeline that was bringing oil from mainland Alaska to the mainland USA, it developed a leakage that overnight it caused spill of more than 200,000 gallons, 4 million liters of oil into the environment. And it was Alaska at Purdo Bay. If you just simply type Purdo Bay disaster, you can see a lot of pictures and also reports about it. And the main culprit there was the activity of sulfur-reducing bacteria, not from outside, but from the oil that was being carried inside the pipe. So, to cut the long story short, low temperature can slow down chemical reactions. Yes, you're right. But this may not necessarily be the case for bacterial activity.
Thank you, Dr. Reza. Dr. Shafi, do you have another question?
No, thank you very much.
All right.
Thank you very much.
Now, when we come to the last but not least slide, my request to you, my friends, is that even if you happen to forget whatever I said during this presentation today, please do not forget this slide. Never ever mistake likelihood with risk. Never ever underestimate the risk of microbial corrosion. For microbial corrosion to happen, there are some important requirements to be present. first you have to have water in liquid form. So if you have water in vapor form, don't go for MIC. Go for any other type of, or any other corrosion processes other than MIC. Water must be in liquid form. So this is requirement number 1. Requirement number 2, this water must have pH and temperature in the range which is okay for bacterial growth and activity. Apart from sulfur oxidizing bacteria that prefer the very acidic conditions, most bacteria like SRB, iron reducing bacteria, iron oxidizing bacteria, etc., they prefer a pH which is around 5 to maximum 730 something. And the temperature must be the temperature range where water is liquid. So this is requirement number 2. Requirement number 3, this water must have enough food in it, enough nutrients in it, like carbon, like hydrogen, like sulfate, nitrate, whatever. These electron receptors must be present in water so that they will start to act as the food source for the bacteria. And last but not least, this water must be in contact with rough surfaces. For example, you have done welding, but you have not done post-weld treatment correctly. The rougher the surface, the higher the likelihood of bacterial attachment and therefore formation of temenos. Low likelihood always comes with high consequence when it comes to MIC. You saw the industries in which microbial corrosion can be a threat. You saw some examples of the assets that actually create, in which MIC could be a case. And it is not something like what you call it, propaganda or promotion for my book. But please do provide this book because of the cases that I have gathered there. You may have seen a lot of corrosion atlas books. They have lots and lots of corrosion examples. But in this book, my concern was to only focus on MIC and MID. That is microbial corrosion for metals and microbial deterioration for non-metals. And I am quite thankful to my friends and contributors who helped me to make this project happen. So far, so good. I again thank you very much, all of you, for sharing your time with me. I hope that you have found this presentation useful, and I'm here to discuss further questions if you have any.
Thank you, Dr. Reza. Thank you so much for amazing presentation and sharing the waste knowledge with us. It was very precious, not just for me, for all materials engineer, chemical engineer, metallurgist, or all scientists or engineer. They are working with metallic materials and they are facing with corrosion problems. So for the last part, as you mentioned, the question and answer sections, I saw that Dr. Javaherdashti raised hand. Please go ahead.
Yes.
Thank you. The second part of presentation also was really interesting.
Oh, thank you very much.
Informatic. Just, I am a little bit surprising that if, for example, we have metal in high humidity conditions, let's say 90% humidity conditions, according to what you said with risk analysis table, that the water should be in liquid phase. But it seems that there should be also MIC for that cases, isn't it?
There could be, yes, because, for example, here, this example has been taken from a wet cooling tower from a power plant where you don't have water like sea flowing, you have droplets of water. Or, for example, here, you have water mixed with bacteria, and most of the time this moisture that you have during to day-night cycle could well form a even thin layer of liquid, which would be enough for.
Okay, you mean that the condensation here means the liquid? Then this is a very important issue, because some people don't consider small droplets and condensation as a bulk water. Yes. Thank you. And here I wrote also in the chat the address of biointerface group on World Academy if you wanted, or other participants, to join biointerface group on World Academies. Thank you.
Thank you very much. Thank you, everyone. I would also appreciate, because for some funny reasons, I can't open up chat here, but if Dr. Tabai, you are kind enough to share this information with me on WhatsApp, I would be highly thankful to you. So yeah, I am quite interested in collaborations with international entities. At the moment, we are working on a proposal. Let me just say a few words about it. I read a paper some years ago about bacterial activity around nuclear power plants. And it has been reported that there could be a very interesting patterns of growth and activity for such power plants. And I am very interested to work on this subject because it is a matter of safety for countries who have such plants. And if anyone is interested, you can always reach me and let me know that you want to participate. And we have actually prepared the proposal, and we are looking for international partners and collaborators. This will be a first ever attempt to academically and systematically explain this phenomena.
Dr. Javaherdashti, Dr. Reza,
yes.
I think maybe Dr. Karapetian, Professor Karapetian is the, I don't know if you know him or not.
No, I don't know. I don't know.
He was for many years the vice president of پژوهشگاه نیرو, you know, the Nero research institute.
Yes, I have worked there. I have worked there. Yeah.
Yes,
but I don't know Professor Karapetian.
Then maybe via Dr. Tabai, we can make a link to Professor Karapetian, who works in پژوهشگاه نیرو and also Polytechnic, Amir Kabir University of
Yes,
Technology.
yes.
On power plants, they should have mainly projects and they might be interested. And
Mhm.
maybe you can also provide similar lecture, but with a focus on power plants for them. Okay, thank you.
Thank you. Thank you very much. Dr. Tabai, I thank you particularly for accepting the trouble, for organizing and doing everything. That went very well. I'm so thankful to you. And yeah, let's be in touch.
Thank you very much, Dr. Reza. It was amazing presentations,
Thank you.
sharing these experiences. Sometimes it's very difficult for us if we want to go to search it by ourselves.
Yes.
Thanks a lot for sharing with us. Very much appreciate.
Thank you.
I hope to have another meeting or presentation from you. And thanks to all participants. I should mention that it was the session 43 from Material Science and Engineering Club. Thanks to all for being with us. And I will share you the video after the finishing this presentation, and also the recorded voice will be shared in Castbox and also in the telegrams for these clubs. Thanks a lot again, and I hope you enjoy your day or night, and I hope to see you next week.
Thank you very much. Likewise. Thank you.
Thank you so much.
Bye-bye. Bye.